This is a one-step organic synthesis reaction. We're going to hydrolyze this with sulfuric acid as the catalyst. That's going to leave the OH there for vinegar, acetic acid, ethanoic acid, and that group there is going to join on here. So that'll be that there being the ester. And so that is called aspirin. So just doing a quick safety check. We're going to get close to to 10 mils because we're going to use about 5 mils, and almost half of that will be used up in the reaction. That will be dispensed by the teacher in this case. The rest of it can be disposed of in the bin, and the rest, it's not of great concern. Just if you have left over too much acetic anhydride, you need to collect that. So the first thing you're going to do is measure about 2 grams of salicylic acid in a conical flask and record that. That'll come with our calculations at the end. Then the teacher will add 5 mils of acetic anhydride. We'll see in the calculations later, this is quite rough. Then the teacher will add 5 drops of concentrated sulfuric acid, put it in a 70-degree water bath, and that's for about 20 minutes in this method. I don't know if there would be an ideal better method, but we'll talk about that later. And then you let it cool. So that's to precipitate out as much of the aspirin as possible, and so we can collect it. And so at this point in time, we kind of use room temperature water. We'll try to make it cold, but as the reaction progresses, how cold everything is questionable. The method we're using also says to use cold water, about 5 mils, and add it directly to the conical flask, and that'll help precipitation occur as well. And so here we have a Buchner filter. So it's a filter under vacuum, so it pulls out the water quite well and quite quickly. The key point here is don't empty it too fast, otherwise you'll lose all your product down the side. And everything sort of needs to be cold, which is probably the biggest problem. And so, as you can see, we have some product there. We'll wash it out with some cold water to get rid of all the impurities. And unfortunately, that may dissolve some of the product, which I think is the biggest error. And that there is, you've pre-weighed the watch glass and the filter paper, and then you take a reading with the watch glass, filter paper, and the product, and so you get your final product results. Just to check for purity before we do calculations, what you can see here is if there's an alcohol, a phenyl group, iron chloride, the pH is around neutral, will give you a purple color. You will get other colors at different pHs. And so if it's not pure and there's leftover salicylic acid, it'll turn purple. And if it's mainly just pure, there's no phenyl groups in the other areas, and we assume that's all being washed out, then you won't get any leftover material, and it should be pure and not turn a color. So we're going to add about 10 drops of 1% iron chloride to all of these. So first we just get 5 mils of distilled water, put the pure product in there, mix it, and you can see it's nice and clear. So we have a nice pure product. Just to test that the iron chloride works, we put pure salicylic acid with 5 mils of distilled water, and it goes nice and purple. And then we use the filtrate, the stuff that came at the other end of the filter, to see if there was any leftover reactant. And you can see there's just a little bit of excess reactant there. It's gone just a tinge of purple. And so that looks all good as far as purity is concerned. Just moving on to the calculations now. Now I put the uncertainty there because they may be useful. It turns out they're not that useful, to be honest, for this particular one. So that was the mass of salicylic acid by tearing the balance. And then we worked out the mass of the acetic anhydride by using the density. And so we've got the ratios as all 1:1:1. And so that's how many moles of salicylic acid and acetic anhydride we used. And so as it should be, the excess reagent is acetic anhydride is the excess, and the salicylic acid is the limiting reagent. So doing 1:1 mole ratio, then that gives us this many moles of aspirin. So we should get about 2.68 grams. Started off with this, and then we minused it with the product. So we ended up getting about 1.437 grams. And so we got a yield of about 46%, which isn't too bad because, as we'll discuss in a second, according to AI, most results publish about 50 to 75% yield. So just doing another AI to be a bit lazy. What are possible problems? Incomplete reaction. I don't think so. We gave it 20 minutes and 70 degrees. Loss due to filtration. Actually, one of them was a complete failure because it was just all poured in and it went out the edges. This is the big one, I think. Recrystallization. I don't know whether it was cold enough and left long enough to all precipitate out. This one could be. It's reversible esters, so it could have gone in the opposite direction and formed other products. Being not dry enough would have made the results too high, actually. And it's typical with AI. They miss the most important one. I get this all the time when I check for AI for errors, so be careful, guys. AI is useful for all those little ones, but it usually misses the most important one, which is the solubility. So if I looked this up here, and that's the solubility of aspirin in water. So I've got to change all those units. We're often using just 25-degree water. So 0.3 grams we're using maybe less than 100 grams of water, but the solubility is 0.3. And our answer is only 1.4. So we're looking at a 30% error there and then, and almost accounts for 100% of all our error. So obviously it not being cold enough to precipitate out, so it's coming through as liquid. You washing it also dissolves it further. So the whole thing's all about getting it as cold as you possibly can. So that should be the emphasis, and the yield will go up dramatically once we realize that everything's it's not precipitating out and then it's getting redissolved. That would be the big issues. The other things that I'm not 100% certain on is how much we're destroying it with the hydrolysis and how long it needs to react. But without a doubt, this is a huge red flag. Not picked up by AI as you'd expect, okay? AI doesn't know what it's doing.